Session 19, Unit Testing Framework, Linux Application Programming Series. What you will learn, what is the agenda, what you can expect from this lesson. Unit tested versus system testing. Brew your own framework. Testing with C unit test framework. Testing with embedded unit test framework. And testing with expect. In short, there are 2-3 examples which will be discussed in this session for testing your applications. What you can expect, the takeaway should be not only these specific tools, but also an idea that what testing is and how actually the testing works because of the real examples which will be discussed in this. So definitely that will give you a direction to explore more testing framework. Something like learn one car how to drive, learn car driving with one model make, and then you can take another any other model in any other car and you will be able to drive. Writing software is difficult. Even when on building on outstanding operating system like Linux. The complexity of the software grows as the size of the system grows. But even when developing smaller systems, the problems can still find their ways in. I remember my C language project which I boasted about on the day one, that I developed a notepad editor in C language. It appears simple, but trust me, these were around 50,000 lines of code in that program. It took me nearly 5-6 months to complete that project. So when you get into the project, you start working on it, and as it grows, think of that I wanted to add more features and more power to that. It would have taken much more time. Equally big was my Lotus 123 package. However, I started with the simple application like painting the screen, then drawing border to the screen, then cleaning up the screen, then displaying menus, then writing functions. I never used any library function including printf or scanf. I never used those functions. I used capture the key stroke using the ASCII value of every key being pressed. So I could capture even caps lock key or num lock key or whatever keys were there, and we used to handle the registers directly. I still remember some of the things, but it was quite around 30-year-old project. I don't remember everything all, but yes, I know how it worked and how I decided, how I approached to the project. First I created some libraries in header files and constants and literals and everything. Then I created some mandatory functions, included them, put them into a file, into library files. Then I included my library files, and then my simple first program, that main program was not that difficult to handle. So here the same thing being mentioned, even when you're developing smaller systems, problem can still find their way in. This is where testing comes in. Performing tests on software can identify shortcomings, allowing us to fix them. If our tests are repeatable, we can easily retest our software once we have made changes to it. That's called regression. Called regression testing. That means testing the software after making some changes into the software. In this session, we'll look at number of available open source unit testing framework and how they can be used to improve the quality of our software, of course with the examples and everything. Awk probably was the first session where there were not much of the examples compared to other source code, because it was more of a command like SED. So SCD is just like a command, so awk is also a command. So not many examples were discussed, but these kind of tools, the unit testing, they require sample applications also, framework also, and testing output also. Therefore, this will be followed by better and comprehensive hands-on experience, which you will try after I finish this. Unit testing. Unit testing is testing of specific user level features of the software. We simply test for what the system would do. The components of our system can be broken down into smaller modules called units. So if you look at system testing is end-to-end testing. You test the overall functionality of the system, what input the system will expect, what output you will expect from the system. That is system test. When it comes to individual components of the system, this is your system which is made up of multiple components, component A, B, C, D, E, these are different components, they are connected with each other, and we want individual components to be tested, like component A independently tested. Then these smaller units are called modules or units. These smaller modules are called units, and we can perform testing on these units. So unit testing assumes more knowledge and insight into the software to be tested. That is correct, because the system testing can be done by a novice user. Like I told you, write a program to add number. Recollect your day one lecture, the first program I gave you, to add two numbers. And I behaved like a duffer user. I did not know anything. I behaved that way, and I tested your program on just the number of my choice alphabets or characters of my choice, rather than what you expected me to type, maybe 10 or 20, maybe 13 or 30, 13 or 50. But I typed something different. So that end-to-end testing, system testing is different approach. Whereas the unit testing, the testing of the unit themselves require the knowledge of the unit, knowledge of the module, knowledge of the software, knowledge of the development methodology you used. So unit testing assumes more knowledge and insight into the software to be tested. So unit test address units of a software system, and therefore address internal behavior of the system, and you get down to the level of units, means the functions. So this is unit A, unit B, unit C I was referring to, which make the entire system. Let's say that our software system include a queue unit that was to be used for internal task communication. We could separate this unit from rest of the system and test it in isolation with a number of different tests, like the behavior of the queue itself. What kind of data it is expecting? Are we sending the same kind of data what it expects? Maybe provide, because one more aspect I must tell you, that any test is based on dry run. Go back to your old programming days, the approach. What was taught to you in your programming days? First was the algorithm, no program. Then the flow chart. Then the pseudo code, if you actually followed the right methodology of learning programming. Algorithms, flow chart, pseudo code, and then actually the code. In code also, I am sure we have learned with the dry run, with the sample data, dummy data, and tried with expected results. Because computer does not do anything on its own. You first have to convince yourself that yes, manually it is working. Computer can just make it faster and easier for you. If you do one test 10 times, computer will do it 100 million times without any problem. However, if I ask you to count up to 2000, I guarantee that you will not be able to speak without any problem, without any single miss of the number or any error. Just counting 1 to 2000, 1, 2, 3, 4 up to 2000, there are chances that you will make mistake, because when you speak as a human, our mind diverts, we commit errors. So that is something where computer will not do. Therefore, first thing is the dry run. If you have the data in that unit test also, what you will be doing is you will be sending some data and then waiting the expected result. If the results are as expected, then your unit test fast. And that's how you will see in the examples also. We could separate this unit text Q unit from rest of the system and test it in isolation with a number of different tests. This is a unit test since we are addressing a unit of the system at a time. We also commonly consider how the units are constructed and therefore test this knowledge, and that is called white box testing. That means you know what you are testing, you know what your code is expected to do. So you know the working of the code and you are testing with the data. So you already know what you are testing, you know what the expected results you are expecting. That is called white box testing. This permits us to ensure that we have tested all the elements of the unit. Therefore, a unit test simply invokes the unit's API and verify that given stimulus produces as expected result. So, this is the sample data we put inside the unit test, and we expect the output from the unit, and this makes the entire unit test. So, in a unit, we insert sample data, we expect sample output, and we verify if we are getting the same output, then we say the test fast. Unit testing frameworks. Some of the unit testing frameworks are Brew Your Own, means write your own, means create your own. The cut system, which give you some libraries and functions ready to use. Embedded unit test and expect. Brew your own, write your own. Let's look at simple architecture of testing a software unit. Consider that we have a simple stack module with an API consisting of simple functions, like this is our structure, type def struct for our stack, and we define a stack and we write these functions stack create, stack push, pop and destroy. And we are passing pointers and we are specifying the size and the elements here, like a create stack of these many elements, push an element, pop an element and destroy the stack. So we have these prototypes to create or to manage our stack. This is our sample example for our consideration. This simple last in first out stack permits us to create a new stack, push an element on the stack, pop an element from the stack, and finally destroy the stack. Now we can write a module stack.c for this simple module to implement this along with a header file that is stack.h, which have our stack definitions. So let's look at the simple regression that when built with this stack module can be used to verify that it works as expected. Since there are many individual tests that can be used to validate this module, we'll concentrate on just few of them to understand the approach, because our focus is the direction, the approach, how actually the testing works. That is our objective. So now we include our header file stack.h. This is given in stack.c in your session 19 subdirectory. Stack create, we are creating a stack with stack pointer size. If size is equal to 0, stack size greater than 200, return with negative. So that means if you are passing 0 or more than 1024, we are returning. And then stack storage, allocate the memory of size stack, and stack storage. Where are the tests? We look at with some sample data, because this is what we are doing is a stack created, maximum stack size, index, assigning the values, stack push, this is our function, stack pop, this is our function, to push an element and to pop an element. These are our functions which we want to test. Are they performing as they are expected to do? Are they doing the job what they are expected to do? We are going to validate these, and that is going to be our unit test. So this is stack destroy. So all the functions are called in this main program: stack create, push, pop and destroy. This is our main program. How do we write test for this program, unit test for this program? How can we ensure that before we create a binary, we write a program that verifies the working? This is our header file which is used for this purpose, stack.h, which defines the structure of the stack, which have integer and integer storage, right? And the 4 prototypes of our 4 functions: create, destroy, push and pop. Regression test. Now if I want to create a test for this stack program, what would I do? That's quite simple now to understand, and you will find it, okay, that's so easy. Because what we are trying to do is we'll pass some sample data and we'll see if it is returning at expected or not. So look at this test. Test 1, creating a test. By default we are treating it failed is equal to 0. So stack create with 0, 0. Check the results with this. So what check result is doing? Check result is taking test number and we are passing a result, and then we are verifying a result is equal to 0. Printf failed, test number is failed, else we are saying it is passed. Now result is equal to 0. So result we are passing here, the second value is the result. So that means if we are, see what this function is doing, not doing anything big here. This is doing, we are passing an element value of 0 and we are expected that stack will have the value 0. Means we are passing a value and the stack should be created with a value of 0. That's what we are testing here. A result, if the value is actually same, then our stack is created, the test passed. We are passing pointer also, stack create, my stack, and passing it should return a value 0. So this is what value we are passing and what we are expecting back. If it is returning, it is expecting that much, that means our stack is successfully done. So this is our regression test. If we make any change in the program and if we pass this value and get the return value the way it is given in this program, that means our stack is successfully created. Like for example, stack result, check result 6, my stack maximum is this, and if it is expecting this value, like if we are passing 6 we are getting that, that means our stack is successfully created and is working program is fine. So what we are doing in this test, let's understand. We provide 2 infrastructure functions as wrappers. First is a simple main function that invoke each test, and then the result checking function which is used here. Result checking function. These are the 2 functions which are created used here. Result checking and the main function that invoke each of these tests. So this test function is our main function which is invoking these tests. We declare a failed integer which will be used to keep track of a number of actual failures. This is used by our main, which allows it to determine if the regression test passed or failed. The check result function takes 2 input, the test number and the individual test result. If the result is 0, then we mark the test as failed. incrementing the field count, otherwise the test is passed. We call API function with a set of input data and then check the result. In some cases we pass good data, and in other cases we pass data that will cause the function to exit with a failure status. In other words, we are doing a dry run through the program only, through the function only, passing the values, verifying that these values are passed successfully or not, like maximum, minimum, out of range data, the stack is behaving as expected or not. We are just passing some good or bad data. If you look at carefully, line number 24 and 25, that is 24, 25. This is what I explained. Test stack creation with a 0 stack element. Here that we test the return variable with -1, since that's what we expect for this cause, for this case. If the return was not -1, the result will be in 0, indicating the test failed. Otherwise, if the return is -1, the expression reduces to 1 and the test will be pass. Same program. Our regression also explored the stack structure in order to ensure that creation function has properly initialized the internal elements. At line number 36, we check the internal state variable to ensure that it has been properly initialized with the stack created. And if you look further in the same program, in the end of the simple regression, we indicate whether the entire test passed or failed. That is our main program. And this is the last part of the program. Last result is this, and we are out of 10 programs, how many of them failed and how many of them passed. So if failed is equal to 0, printf test1 passed, else printf test1 failed, and what all passed or whatever failed, you see that. So failed is equal to 0, and then we are calling this test1 function, indicating that sorry, excuse me. So after that main program is called, it will call the function. So calling all the rest of the functions also what we declared into stack.h and stack.c and regression.c to verify the creation of the stack and working of the stack. Our main program simply calls our regression test in order clearing the failed count. In the stack module source, a stack creation and destruction can fail in multiple ways. This test try each of them. Now this is what I am running this test. I run this program and you see the test 0 passed, test 1 passed, all the tests are passed. Finally the test 1 is passed after I compile this. While the method is quite simple, but yes, it is very effective, and it permits the quick validation, revalidation of a unit after the changes are made. Once we have run our regression, we can deliver it safely with the understanding that we have less likely to break the software that uses it. So what is the summary of so far whatever we discussed? 2 points to be noted carefully. 1, we should know ourselves what our software or the unit of code is expected to return in different scenarios. Recollect that that program is still valid and important and relevant here. Think of the same program what I was talking about. I was talking about two programs to add. Think of that same program and relevance of that. That program taught you how to think negative and how to consider each of the scenarios in your test, include your scenarios in the test, and write test before you actually deliver the program to me. The two program to add the number. Same thing is explained here with stack example, and we are performing some test on our own program before we hand over that yes, program is working fine, I have verified it. The C unit test system or CUT. The C unit test or CUT for short is a simple architecture of building unit test application. It is open source. It's available on sourceforce.net. I have downloaded it from there itself. CUT provides a simple environment for integration of unit test with a set of tools that are used to put together tests and then build a main framework to invoke and report them. CUT parses the unit test files and then builds them together into a single image, performing each of the provided unit tests in order. It provides the utility written in Python called CUTGen, that is the generation of the code files. It will generate the files for you. .py, I have shared that in the folder. It is included in your source code folder. The utility parses the unit test source files and then builds a main function around the tests that are to be run. The unit test files must be written in a certain way. So this is example. The unit test example written for CUT. Let's walk through an example that verifies the same program, that is stack, with the same set of function push and pop functions of our stack example. How can we do the same in CUT system, C unit test system? CUT presents a simple interface that we build to. So this is our test1.c modified version, test_1.c in your directory, that is not ch24, that is the folder name is different. This is wrong. It was actually my original source code. So you know there will be file test1.c, stddio.h, stack.h, cut.h, you include that file. Stack, we are creating two stacks here, my stack 1, my stack 2, and this is how you are writing the function cut bring explode. What this function is, we'll understand that, and then print stack test bring up called stack create, and stack create, we are creating two stacks. This is 5, this is another stack created, and stack 2 creation, this is stack 1 creation. We declare our locals at line number 5 and 6, for which we will perform our test, and then 4 functions that serve as interface to C unit test system. The first 2 functions to note are initialization, that is cut underscore bring up explode, line number 8 to 20, and then second part is the takedown post test execution, that is cut takedown explode, line number 74 to 85. They are actually to destroy. Explode is to create, takedown is to destroy, that is destruction. The cut framework calls the bring up function prior to the test start, and once all the test functions have been performed, the takedown function, means destroy function, will be called. We simply perform our necessary initialization But we also perform unit testing here to ensure that the required elements are available for us in the unit test. Similarly, in the takedown function, which is called once, all unit tests have been called, we destroy our stack as I told you. But we also check the return status of these calls. Are they destroyed successfully? The unit tests are encoded as function with the prefix of CUT, underscore underscore CUT. This allows the cutgen utility to find them and calls them within the test framework. As we perform the necessary elements of our unit test, we call a special function called assert, which is used to log errors. The unit test examples written for cut. The assert function, we are calling here assert every time for dropping or successfully creation or this. This function also have two pieces, a test expression and the string emitted if the test fails. The test expression identifies the success condition, and if false, then test element fails. In some cases, we have multiple tests for each API element as shown in line number 64-65. Values, return value 0, stack pop failed, value 101, stack popped wrong value. Means you expected, if you are getting 101, for example, we are comparing, if you are getting 101, then it popped wrong value. You expected something else, but you got something wrong. So these are just, these functions are just telling you that what value you were expecting, what value you passed, what value you expected. Now let's look at how we make this an executable test. We'll use our CLI, building this example for demo purpose. 3 files are needed from the cut system. cutgen.py, which is there in your source code directory, that build the unit test environment, given our set of unit test source files. This is actually a Python utility, Python file. So Python interpreter will be necessary on the target system where you run this. 2 other files are cut.h, which you will include in your program, and libcut.inc, which is ultimately linked to our unit test application. The first step is creating the cut unit test environment. This create C main and bring together the necessary APIs that must be used by the unit tests. The cutgen utility provide this file for us. So when you write cutgen.py and you write your program, this will create this file cutcheck.c. You redirect it to this file, and this will this file will be created. So we try, this is the command I tried on my system, cutgen.py test_1.c and cutcheck.c. When you run this, when you check the source code of this cutcheck.c, it will generate the source code. This is actually a C program. So it is doing nothing but calling the functions together, like bring, explode, push consumption test, and the pop test, and then take down. So all the 4 functions are put together and called in a right direction. So first external declaring them and then calling them. The automatic generated files from the cutgen simply brings together the unit test presented in our unit test files and calls them in order. So what actually it is doing? Nothing much except that calling all the functions which are there in our program, putting them together so that they are called. We could provide multiple unit test files to cutgen, which would result into additional unit test functions being invoked in generated files. Finally, we simply compile and link the files together to build a unit test image, that is binary executable file. So this is what we are doing. We are compiling stack.c, test1.c, check.c, and then we are running it, and you will see the results here in my case. Test complete. So you will see how they are called and what value is expected, what value is returned. This implies that automatically generated source files, unit files, and the source to test the stack.c program. Embedded unit test example. The embedded unit test framework, that is Embunit, is an interesting framework that's designed for embedded systems. The framework can operate without the need for standard C libraries and allocate object from constant area. Embunit or embedded unit also provides a number of tools to generate test templates and also the main function for the test environment. This framework is very similar to CUT and provides a useful API for testing. Some of the test functions that are provided with the Embunit: test assert equal string, expression plus actual value, what you expect from this expression, assert and failed string compare, then equal integer actual value, assert on failed integer compare, assert if the point is null, if pointer is not null. So we have these functions to for this purposes in this embedded unit test framework. Unit test code for this embedded unit framework. Let's now look at the unit test coded for this framework, and then we'll look main program that sets up the environment. Again, all sources code is provided to you for your practice, for your understanding. In this program, in this example, a minimal unit test for Embunit is shown, and this is our stack test. Again, our stack remains the same, concept remains the same, so that you understand, and it is stack test.c. It is available under source code under EMB folder. So when you switch to this folder EMB stack test, you will find this, and you have to include these files: Embunit, unit.h, and stack.h, studio.h, stack.c, and here you are declaring, and then tear down, test init, and then test push and test pop. At line 1 we include the embedded unit test header file, that is embunit.h. We then define two functions that are called before and after each unique test that's identified to Embunit. Setup at line number 7 to 10, that is static void setup, and tear down at line number 12 to 14, tear down. Now after that we define our individual unit test, line number 17 to 51, line number 17, test unit, test push pop, and then test stack destroy. We are defining our functions. The stack push pop, if you see, we are trying to push value, we are trying to push value, we are trying to pop value. So whatever value we are pushing two values and we are popping two values, and we are comparing that value should be written as expected. If we get what we pushed, that means the test is complete. Three tests are defined here. First test is called test init. The first is called test unit 17 to 22. This 17 to 22. After that we are using second test is called test push pop 25 to 42. The third is called test stack destroy 45 to 51. We perform an action and then test the result in each of these tests. In this case we use Embunit provided test assert equal int function to check the response, and if the test fails, assert fails, an error message is printed. Same in the last part of the program. Finally, we have stack test tests. Finally, we specify the unit tests that are available within the test function, line number 55 to 66. This is done in context of a text fixture structure. Like what we have is new test fixture, test init, test fixture, test popup, test fixture, test destroy. So if you look at, we are calling initialization, push pop and destroy in this embedded unit text fixtures. We call them as fixtures. So this is called, and by calling this text fixtures, we are setting up the entire test. We define fixtures as simply an array that's initialized with provided functions and function names. We then create another structure at line number 62 to 63 that defines our test, setup function, tear down function and fixtures. That is our list of unit tests. This new structure called the stack test is returned to the caller. Now the main program. Our main program is simple: test runner start, test runner unit test, run test. That is the function which we defined in the previous page, and test runner and return. So this is our test runner which is calling and doing the test. This is defined into main.c under embed. So this is a complete walkthrough example available in source code directory to run the tests. Our main program provides the means to invoke the unit tests. We include embedded unit.h for types and symbols. At line number 3, we declare our previous function which creates the text fixtures array. We call the test runner start function to initialize the test environment and then invoke test runner run test with our unit test fixtures unit function, that is stack test tests. This invoke all the unit tests we created. Now you see the entire tree or hierarchy of the test and the main function, how the other functions are called and how the entire setup is working. When done, we call the test runner end, which emits the statistics about the unit test, including the number of tests run and the number of tests which failed. Building the unit test within embedded unit simply involves compiling and linking our source files together with the embedded unit library. In order to find the embedded unit library, we must specify its location. Building and running the unit test. We see that setup and tear down are called 3 times each, before and after each of our unit tests. In the end, we see that the embedded unit test environment reports that 3 tests were run and 1 failed. This is a run of our example. So that's clearly we are calling it stack test, setup called, test unit called, tear down called and dot setup called. Then after that again push pop, and you see this was something is wrong here. So this test failed, other are successful. So run 3, failed 1. Then we have expect utility. This has found a wide use in testing domain. It is an application that scripts programmed dialogues with interactive programs. Using expect, we can spawn an application and then perform script consisting of dialogue with the application. This dialogue consists of series of statements and expected responses. In the test domain, the statements are stimulus to the application, and the expected response is what we expect from a valid application under test. The expect utility can even talk to multiple applications at once and has a very rich structure for application testing. Like this is testing a normal BC calculator with expect. Install the expect with yum install expect -y. This will install the expect utility if it is not installed, and the source code is given under expect folder. Test BC. Test the calculator. So what we are doing, see the same thing, nothing complex here. We are passing the result, we are passing an expression and we are passing the result, what to expect. So we are passing the expression and the result, and if we are getting what we provided, if they are matching, then it is passed. At line number 14, we spawn our test process, that is spawn BC. We consume the input from BC startup by expecting a string warranty. We then emit an indicator to std out indicating that we test has started. That is line number 17. At this point, we begin our test. And in line number 20, 21, 22, what we are doing? Using send expect procedure, we send a command to the application and then provide what we expect as a response. For a calculator test, we provide some simple expressions from line number 20 to 22, followed by a slightly complex function example, which is line number 25, 25, 26, 27. At the end, we emit the BC quit command, expecting the end of the file. So this is the test run. So test starting, 2 to 4, 6, 2 multiplied by 8, 16. So all the tests are fast, and you see the result, test complete. The expect method differs greatly from our unit test examples, but still it's a very powerful mechanism, not only for testing but also automated tasks, even those on remote systems. So the summary of this lecture, what we have understood: the unit testing discipline has improved with open source tools. These tools provide efficient and simple mechanism for unit testing. In this session, we explored unit testing concept and investigating some of the methods like cut, embedded unit testing, and expect, and brew your own, even writing from scratch. We first reviewed a brew your own method for testing that was simple but got the job done. We then reviewed two open source tools for unit testing, the C unit test system and then embedded unit test system. Don't stop here, team. I must tell you that these are only two examples. There are multiple examples available, multiple options available for unit test framework. Finally, we took a quick look at expect and its capability